So good afternoon, everyone. Welcome to the first meeting of THEP Journal Club of this year. Today, we have our department PhD student, Miss Mandeep Kaur, as our speaker. She would be talking about Higgs decay to 4 leptons and QCD corrections. So I request Dr. Amresh Shivaji to be the moderator for this seminar. So,
okay, Mandeep, you can start.
Okay, sir. Hello, everyone. Myself, Mandeep Kaur. Today's my talk is more or less is like my annual review seminar, and the topic of my today's talk is QCD corrections to Higgs to 4 lepton decay. Here are the contents of my talk. Firstly, I start with a brief introduction and how to look for the new physics and hints for the new physics via indirect methods. And a brief intro, then I give a brief intro to the Higgs physics and Higgs boson production and decay channels. And then I discuss for this particular decay channel Higgs to 4 lepton and the motivation to look why we are mainly interested in this decay channel and what is the purpose of studying the QCD corrections to this decay channel and all, and then how we calculate the amplitude for this process, and I briefly discuss about the other things which are related to that. So let's start. As we all know that standard model of particle physics is the quantum theory of matter and energy that surround us, and the last piece of this model was the Higgs boson, which was discovered in 2012 at the LHC by the CMS and Atlas collaborators. We know that standard model is a very good model and it can perfectly explain most of the experimental results, but there are many questions which it leaves unanswered. Because of that, it sometimes appears to us like an incomplete model, or some like it doesn't predict the masses of the fundamental particles, including the mass of the Higgs boson and all other things like the dark matter, dark energy, and neutrino masses are not included in the standard model also. So all these things points out something like standard model is just an approximation to a more general theory, and that motivate us to look for the physics beyond standard model, which we know as the BSM physics. So how can we look for this new physics? To look for this new physics, there are mainly two ways. One are the direct methods and other one are the indirect methods. Direct methods are those in which we produce these BSM particles directly at the colliders, but there are the two possibilities there. One is that those BSM, the energy scale of the BSM, if it lies in the range we are doing the experiment in the energy scale we are doing the experiments currently, but we have scale is in the range of current collider energy range. And second possibility is that the BSM energy scale is much larger as compared to our current energy scale at which we are performing the experiments. But even if the BSM energy scale lies in the range of the current collider energy range, we haven't seen any sign for the new physics at the collider. So it points out something like that those BSM particles either they do not interact with the standard model particles, or second possibility is that even if they couple with the standard model particles, but their coupling is so weak that our current with the that is out of we can't detect with the help of the current technology we are using and the colliders. And in the second possibility, if the energy scale of the BSM reside on the very large energy is very large, then that is also out of the reach of the current technology we are using at the colliders. So in that sense, these direct methods for the detection of the new physics are not accessible. So we go for the indirect methods for to look for the new physics. And what are these indirect methods? In which BSM reveals itself by participating in the standard model processes virtually. That I will explain in my next slide, that how what are these indirect methods are. So how can we look for the new physics via the indirect methods? That we can understand with the help of a simple example of 2 to 2 process. This is a 2 to 2 process in which all the particles which are participating are the standard model particles. So this is a tree level diagram for a 2 to 2 process, or we can calculate the differential and total cross section for this process in the perturbation theory and include all the higher order diagrams which are incorporating all the particles of the standard model, and we get the total cross section. Like let's consider the observables total cross section for this process, and then we compare our theoretical calculations with the experimental measurements. If there is no BSM particle which is participating in this process, in that case our theoretical calculations will match with those of the experimental one. But in case when there are some BSM particles which can interact with the standard model particles, and then they can participate in this process virtually, something like this. These are SM particles. This one is the BSM. And if the BSM scale this if the BSM particles are which are running here, they are very heavy, in that case this process is something look like this: effective interaction. So because of the presence of these BSM particles, these kind of diagrams also these kind of interactions are also going to participate in the original 2 to 2 process. So as a result of which uh, uh, because of the presence of these new physics particles, our standard model predictions deviate at the level of cross section and differential distribution, etc. It means that, like, now this new type of interactions also participating in the original 2 to 2 process. So when we measure experimentally, these type of interactions are there, but when we do the theoretical calculation by only including the standard model particles, then sigma for standard model theoretical calculations are not going to match with the experimental one. So there must be a discrepancy between the theoretically calculated values and the experimentally measured values because of these kind of effective interactions. And these kind of discrepancies between the theoretically calculated values and the experimentally measured values gives a clear hint for the presence of the new physics beyond the standard model. But if we want to be very clear that this discrepancy is only because of the presence of these BSM particles and not because of the any other reason, then we have to be very precise on the theoretical side, that is the for the calculations of the standard model observables. And on the theory side, when we precisely calculate uh, uh, any observable for any process that involve the inclusion of all significant higher order diagrams contributions to the tree level along with the tree level diagram in the calculation for a particular process. And in our present work, we are mainly interested in precisely calculating the observables which are related to the decay process of Higgs to 4 leptons. And we hope that that will provide a better understanding of the Higgs properties and also help for the future searches for the BSM. Before going into the detail of this decay process, Higgs to 4 lepton, I will briefly discuss about the Higgs physics. We all know that Higgs particle was the last piece of the standard model, and that was missing, and it was discovered in 2012, and it completes the standard model. And mass of the Higgs boson is approximately 125 GeV, and it is the only scalar particle which is present in the standard model. And it is the and Higgs field has the non-zero vacuum expectation value, which is around 246 GeV, and this Higgs field is responsible for the masses of all the fundamental particles, and they interact with this Higgs field and acquire masses. And Higgs boson, we know that it is a unstable particles, and it decays into the other particles as instantaneously, and the total decay width for 125 GeV of the standard model Higgs boson is around 4.07 into 10 raised to power minus 3 GeV, with a relative uncertainty of plus minus of 4%. At the LSC, we can produce Higgs, and these are the dominant production channels for the Higgs boson production: gluon-gluon fusion. This one is the vector boson fusion, associated production along with the gauge boson, and associated production of Higgs with the TT bar. Because Higgs boson is an unstable particle, it decays instantaneously into the other particles, and the dominant decay modes of Higgs are Higgs to BB bar and Higgs to WW star. Here star indicates that this W is not on shell, it is off shell. And for and the other decay modes for the Higgs are into two gluons, tau plus and tau minus, CC, charm and anti-charm, and Z and
Mandeep,
Z
one
star.
question.
Yes. Hello.
Mandeep, can Higgs decay into 2W's on shell?
So W mass is like 90
Is that possible?
GeV,
Is
no?
that process?
So it,
Hello.
Mandeep, Mandeep, can you hear us? Hello, Mandeep. What happened to her? Is she
Uh, I think there is some connection problem because she is still there, but
okay?
we just can't hear the voice.
Okay. Um, can one of you call her and check whether it's internet problem or something?
Yes, I will do. So yes, there is some internet issue from her side. So she will be joining back soon.
Okay. Yeah, meanwhile, maybe I can request everyone in the audience that you can ask questions in between if anything is not clear. Okay. So please feel free to ask questions in between the talk.
Hello.
Hello, hi Mandeep. Yes.
Hello. Okay, can you see my screen?
Yes, it's visible. Yes.
I was here.
So you were asked a question about decay of Higgs into WW on-shell Ws. Can you continue
Yes.
from there?
Yes, sir. Actually, the W mass is around 90 GeV and Higgs mass is 125. So if Higgs wants to decay into the two Ws, and the sum of the masses of the two Ws is 180 GeV, so it can't decay into the two Ws on shell. So one of the W must be off shell.
Okay, thank you.
Yes. And these are basically the decay channels for the Higgs, different decay channels along with their branching ratio. Most of the time Higgs decay into the BB bar. Branching ratio for this is like 58%, and then it decay into the W and W plus and W minus, which is like 21%, 21.4. Tau plus tau minus is 6%. Z to Z star is only 2.62%. Out of all of these decay modes, Higgs to 2 photon and Higgs to ZZ star, which ultimately decays into 4 leptons. These decay channels we can see from their branching ratio that they are very rare. Higgs to photon is like 0.227%, and for Higgs to ZZ star is only 2.62% branching ratio for that. These decays are, although they are rare, but both of these decay channel they are very these decay channels play a very important role to study the Higgs properties, and because of the fact that in both of these decays the final state particle like 2 photon and in this case are 2 photon and in this case are 4 leptons, and we can these final state particles, the tagging efficiency of the colliders for these final state particles is very good. We can precisely measure the final state particles in both of these decay modes, and also the reconstructed Higgs mass resolution is very excellent in both the decay modes. But out of these decay modes, we are mainly interested in Higgs to 4 lepton decay channel, and this is also known as the golden decay channel, and it was used for its discovery in 2012, and also this decay channel was used to measure the mass spin parity and coupling properties of the Higgs with the other particles. These are some of the features why this decay channel is important. First of all, it has the excellent mass resolution, and also in this case the signal to background ratio is very high. It is around 2:1, and it has a relative clean background as compared to the other decay modes because of the presence of 4 leptons in the final state, and also excellent precision in the Higgs mass measurements because the final state has the 4 leptons, so we can reconstruct the mass of the Higgs from these 4 leptons. So this is the plot for the number of events with respect to the reconstructed mass of the 4 leptons, and it gives a peak at around 125 GeV, which is the mass of the Higgs, and also another resonance peak at around 90 GeV, which is corresponding to Z star. So Higgs goes to Z and Z star, again in which one of the Z boson is off shell, and then they decay into 4 leptons. So when we reconstruct the mass of these four leptons, we get a resonance peak at Z and another one at the Higgs mass. So this is the importance of this decay channel, and we are mainly interested to improve the predictions for the partial decay width of this decay channel, that is Higgs to Z star to 4 leptons. Branching ratio for this decay channel is 2.62 in 10 raised to power minus 2, that is the 2% that I have discussed above. And the next leading order electroweak corrections to this partial decay width are well known already, and they are of the order of around 2 to 3%. So as we can see from this diagram, this is the Higgs decaying into Z to Z star and then into 4 leptons. So all the particles which are participating in this process, they are all belongs to the electroweak sector. So when we go to the next leading order, only electroweak corrections played important role. So we get the diagrams like this: Higgs going into Z and Z star, which then decay into leptons. So where this is the photon. These are the electroweak corrections at the next leading order.
Mandeep, there is a question
Yes, sir.
from Akash. Akash is asking, branching ratio of ZZ star to 4L is 100%, or there are some other possibilities?
Higgs 2?
Let me read his question again. Branching ratio of ZZ star to 4 lepton is 100%, or there are some other possibilities?
There can be Z can go into the 2 leptons.
He's asking a very precise question. He's not looking at the Higgs. He's saying the ZZ star, can they go 100% times in 4 lepton, or there are other possibilities also?
I think they go most of the time into 4 leptons.
No, but are there other possibilities? Most is one thing. Are there other possibilities? Can ZZ star go into some other final states apart from 4 leptons?
Z can decay into Z can also decay into hadrons.
Okay.
Yes,
Okay.
that is the that depends upon the decay modes of the Z. Z has also, like the Higgs has the more than one decay channel. Z can also has the more than one decay channels. Z also has more than one decay channel, so it can decay into other modes also.
Okay, fine. Akash, is that okay? Okay. Mandeep, proceed.
So at leading order, there are only the particles which are involved in this decay process belongs to the electroweak sector, and at next leading order, so only electroweak corrections plays the important role, and the diagrams like this will comes into the picture. But if we consider, this is the partial decay width for Higgs to 4 lepton, which we know is something like proportional to the modular square of the amplitude for this process. So if we consider all the electroweak and QCD corrections to this partial decay width, and then we get on the right hand side the terms like this. This is the leading order contribution coming from this is the mod amplitude square for the leading order diagram, and this is the, because at next leading order only electroweak corrections are there, so a term like this, and this is the interference term of next to leading order electroweak corrections with the tree-level diagram, leading order diagram, and the terms like this, the interference term of next to next leading order at two loop level, like Higgs to ZZ at one loop can also have the diagrams like this, which then decay into 4 leptons. Which this loop involves, it can involve the leptons, quarks, etc. So in the case where this one loop diagram involve the quarks at one loop level, then at two loop level, we can have the corrections to this diagram like this, in which gluon can connect with these two quark propagators like this or some other way around. So we have the terms at next to next leading order of their QCD corrections are there, their interference term with the leading order. And why um, and I have mentioned earlier that the electroweak next leading order electroweak corrections to this partial decay width are already calculated, and they are well known in the literature. And we are mainly interested to include the QCD correction on the top of electroweak correction to this amplitude for the calculation of this amplitude. And QCD corrections only comes into picture at a two loop level. So if we want to involve the QCD correction, we have to calculate the amplitude for this process up to two loop level. So the amplitude for the Higgs to 4 lepton. Yes.
There are no other interferences of this NNLO QCD corrections with the LO and NLO.
Actually, let me explain this. Uh, we do the calculation in the perturbative expansion. So at leading order, this leading order term, this is like this one. Those terms are also there, but their contribution is suppressed because of the coupling that I can explain. Like this process at leading order, this is the modular square for this process is proportional to E6, that is alpha cube. It is of the order of, so this amplitude square is of the order of alpha cube. And at next to leading order, where diagrams which comes into picture are like this. So the amplitude square will be of the order of alpha 5. So this term is of the order of alpha 5. And when we look for the interference term of next leading order, this one with this one, then it will be of the order of alpha 4. Right? The amplitude for this diagram is proportional to E cube. For this is E5. So when we mod square this one, then it will become E6, which is alpha cube, and this will become E10 mod square, which is alpha 5. But when we take the interference of these two diagram, that is like E8, that is alpha 4. So interference term is of the order of alpha 4. And QCD and NNLO interference term, they are or involve the diagrams like this. This is like E5 GS square. So when we mod square, this diagram gives the amplitude which is proportional to alpha 5 alpha S square. But its interference with the leading order diagram will give us alpha 4 alpha S. So the leading order term was alpha cube. So next contribution will come from this one term, alpha 4 in the perturbation expansion. And after that, there are the two terms. One is alpha 5 and this one is alpha 4 into alpha S. And we know that the strong coupling constant is greater than electromagnetic coupling constant. Alpha is of the order of roughly 10 raised to power minus 2. So this contribution is suppressed as compared to this one. So this gives a significant contribution to the decay, partial decay width as compared to the next leading order electroweak correction modulus squared. So I have summed the other terms in for that their contribution is suppressed. Okay, Pramod?
Yes, fine.
Okay.
Hello,
Hello.
Mandeep.
Yes.
So what is the energy range for this electroweak corrections you are talking about? Sorry, I hello.
Hello.
I mean,
Yes.
we can hear
I'm
you. You have to speak a bit louder, Minati.
Okay, so what is the energy range for this electroweak corrections you are talking about? I think QCD for QCD corrections, it is 200 MeV around, right? Hello, am I audible?
yes. I can hear you.
Yeah. So, yeah. So for electroweak, what is the energy range?
Sorry, I actually I don't know about the energy scale range for the electroweak corrections actually.
So Minati, yeah, I mean, just to answer maybe, yeah. So the QCD scale is 200. It says simply that below that you cannot perform perturbative calculations, right? That's what it means. For electroweak correction, there is no such a scale, at least at low energy. At very, very high energy, you may come across basically such a scale, which is basically known as Landau pole or something. But the kind of energy ranges here, basically the typical energy range is the mass of the Higgs boson, which is 125 GeV. So there is no problem in performing perturbative calculation in electroweak sector as well as QCD.
Okay.
Mandeep, there is a question from Akash. Are you using perturbation theory for computing amplitudes?
Yes, we are only considering the significant from the terms which are actually significant to the total amplitude up to 2 loop level.
Okay, so in one words, it is yes. Okay, go ahead.
Yes. So so we have to calculate the amplitude for this Higgs to 4 lepton process.
Mandeep, you have to speed up a bit.
Okay. So Higgs to 4 lepton process, to calculate the amplitude for this process, we firstly calculate the amplitude for this Higgs to ZZ star, and then we at the that is something like, and then the amplitude for Higgs to 4 lepton, to calculate that we firstly evaluate the amplitude for this Higgs to ZZ star process, and The process involving this process involves the decay of Higgs into the Z and Z star, where I have already mentioned that one of the Z is off shell. And at leading order, there is only one Feynman diagram which contributes to this amplitude, which is shown here. And at the one loop level, there are if we consider all the electroweak and the QCD electroweak corrections at the NLO, then there are the like 259 diagrams are there which contribute to the one loop amplitude. But as I have already mentioned that we are only interested in the QCD corrections which comes into picture at the two loop level. But because the gluons can only couples to the quarks, so at the one loop level all the diagrams which doesn't involve the quark loop, they are get discarded at the one loop level, and there are only these 5 diagrams which will contribute to the amplitude at the one loop level. Now, and at the two loop level, when there is a gluon propagator comes into picture, there are total 21 diagrams, and some of them I have shown here. Because the amplitude calculation involve for up to two loop, we want to evaluate this amplitude, and the direct calculation of this amplitude is very cumbersome, so we use a projector technique to calculate this amplitude. And what is that? As we know that Higgs to ZZ star, the amplitude for this decay process Higgs to 2 G's can be written in the most general form as m mu nu, and we obtain this m mu nu, and then we multiply this most general structure of the amplitude with the leptonic current gmu and gnu, into which these 2 G's will finally decay, and that will give us the amplitude for this process Higgs to 4 lepton. So most general structure of this m mu nu can be written like something like this, where this epsilon mu and epsilon nu for the time being are some 4 operators, which will be finally replaced with the leptonic current, the final step. Here A, B, C are some constants which we call as the form factors, and in order to obtain these A, B and C, we contract this equation with G mu nu, P1, P1 mu, P2 nu, and this epsilon tensor. And when we do that, we got the 3 equations, and we do all the calculations in the d-dimensional space-time, and on solving these 3 equations we get A, B and C, something like this. So on the amplitude, when we apply this thing on the amplitude, we get A, similar for B, and this is for C. So these terms we named as projectors. This is the projector for A, for B, and this is one C. So if we apply this projector on the leading order amplitude for the Higgs to ZZ star, we get A0 corresponding to that A0, and similar by applying these projectors on the leading order amplitude, we get A0, B0 and C0. On the one loop amplitude, we get A1, B1, C1, and similarly on applying the two loop amplitude, we get A2, B2 and C2. So we have this amplitude. I have written it down by factoring out the coupling constants, which involves in this leading order and next to leading order and next to next leading order. Like at leading order, I have already explained that it is for Higgs to ZZ star. It is of the order of E. There is only one coupling of Higgs with the 2 Z's. And at first order one loop, it is like this one. It is proportional to E cube, and at 2 loop it will be proportional to E cube and GS square, which is alpha S. So here alpha is the strong coupling constant. So these are only the significant term. These are only the. So this is the total amplitude up to 2-loop level for this Higgs to ZZ star process, where M0, M1, M2, I've already explained that these are the leading order, next to leading order, next to next leading order amplitudes, and these are all in terms of A, B, and C's. And to obtain this A, B, and C, we want the tree level, 1-loop and 2-loop amplitude on which we will apply these projectors, and that amplitude we obtain with the help of this package, QGraph package. We obtain the amplitude from that, then apply the projectors to get these A, B's, and C's. And because this whole process amplitude calculation involves the loop diagram, so there are some tensor integrals, and in order to evaluate them we have to convert them into the master integrals, and we use the light red package for that. So after all doing all this, we get the final amplitude in terms of these scalar master integrals, coupling constant, and different masses and dimension. D is also A, B's, and C's in terms of A, B's, and C's in short. So we then the final amplitude for Higgs to 4 lepton we obtain by contracting this mu nu with the leptonic current Jmu and Gnu, and we square this amplitude. These are the only 3 significant contributions which will come to this Higgs to 4 lepton amplitude. This is the leading order. This is the interference term of the 1-loop diagram with the tree level diagram, and this one is the 2-loop diagram interference term with the leading order diagram. So this is in the perturbation expansion in terms of alpha. We can see this is alpha cube, this is alpha 4, alpha 4, alpha S. So this squared amplitude is the function of the is only in terms of A, B's, and C's. So only all we have to do is only to obtain A, B, and C, and then we can obtain this amplitude. So after obtaining the amplitude, we have to make some checks. Like I have already mentioned that the amplitude calculation do involve the loop diagrams, and so it is supplemented with the UV and IR divergences, and IR divergences are mainly of 2 types, real one and the virtual one. And there is a theorem in the QCD which is known as the KLN theorem, which which says that if we sum over all the real and virtual diagrams, then all the IR divergences are get completely cancelled out. And but in our case we have seen that there are no real corrections to the amplitude at the 1-loop level. Like at 1-loop level, the real corrections to the diagrams will. This is the 1-loop diagram for Higgs to 4 lepton. And at 1-loop level, the real corrections are like this one, where the final state will be Higgs to 4 lepton plus a gluon, or a jet we can say. But there is only one gluon which is connecting to this loop. So as we know, this is a fermionic loop. So when we calculate the amplitude, there will be a trace over this loop, and there is only and the coupling of quark with the gluon involve Gelman matrices lambda, like if color is a, so the trace will involve that like the trace is over this trace will involve the trace over this Gelman matrix lambda I, and that is 0. So there are no real corrections to the amplitudes at the 1-loop level are possible. So our amplitude is free from any kind of IR divergences. So we only have to deal with the UV divergences in our calculated amplitude. So we have made some checks to look for the presence of the UV poles in the form factors A, B, and C at the 1 and 2 loop level. And here I have represent the results, numerical results for that. And the values which are used to obtain these results, I have used that top quark mass is like 173, mass of Z is set at 91, and Z star is taken like 35 GeV. And we observe that at one loop level. And what is this axial and vector part of A1? A1, I have explained that this is the form factor for one loop amplitude. And because that at one loop level we have the diagrams like this, where Z is connected to the quark loop, and the coupling of Z with the quark is something like gamma for this mu CV minus CA gamma 5. So it has a two part. One is the vector part, other one is the axial vector part. CV is the vector and C is the axial part. So A1 axial is the form factor that is proportional to the axial coupling of Z with the fermion, that is represented by the GZ square here. So when we look for the UV poles, we observe that the axial part of A1, it has the UV pole of the order of 1 by epsilon, while the vector part is UV finite. And similar checks when we made for the B1, the axial part as well as the vector part for B1, they both comes out to be finite as they are expected. And C1 is when we sum up over all the diagrams, C1 comes out to be 0. And similar kind of checks we do for the at the two loop level. And we have we observe that A2, this is A2 that represent that it is a form factor for the two loop, and its axial part have the UV pole of the order of 1 by epsilon square and 1 by epsilon, which is expected because the axial part of A at one loop level, it has a pole of the order of 1 by epsilon. And when we go to the higher order, the like when we go from one loop to two loop, the order of pole will increase. So because at one loop level it has the pole of the order of 1 by epsilon, so at two loop level we expected it to have the pole of the order of 1 by epsilon square, and it comes out to be like that. So it has the pole of 1 by epsilon square and 1 by epsilon. And vector part, because at one loop level it was finite, so we expect that at two loop level it only should have the pole of the order of 1 by epsilon maximum. But in our calculation, the coefficient of 1 by epsilon square is not too small that we can neglect it. That we are checking that why it is so. Still, we haven't find the reason for that. And similar checks we have made for B2. This is the result for the axial part, because B1 was finite for both the vector and axial part at one loop level. So at two loop level, we expect only to have the pole of the order of 1 by epsilon, and it comes like as we have expected. Here the 1 by coefficient for 1 by epsilon square is like 10 raised to power minus 4, 1 into, and in vector part it is like 2 into 10 raised to power minus 5. So we can neglect that. So it has the pole of the order of 1 by epsilon at two loop level. So we have observed that the form factors are UV divergent, and because our amplitude M is in terms of A, B's and C's, and because these are UV divergent, it means that our amplitude is also UV divergent. And if we want to construct any observable from this amplitude, it means that also comes out to be infinite, but that can't be the case because we know that all the observables are always finite. So it means that we have to get rid of these UV divergences. So what is the next step? So we want to remove those UV poles from the four factor. For that we have to do some procedure that is known as the renormalization that we do to remove the UV poles. And in our case there are the many different techniques to do the renormalization, and we are using this MS bar scheme for the renormalization. And to do the renormalization we have to add the counter terms which ultimately counter term diagrams to our actual amplitude. And the when we add all these counter term diagrams to the original amplitude, we expected what is expected that all the UV divergences are get cancelled out and we get the finite result. And these are some of the tree level and one loop counter term diagrams which I have shown. So for the time being we are calculating the amplitude for these counter term diagrams, and then we will add this amplitude to the our UV divergent amplitude, and we'll see that whether our result will be finite or not. We are still working on this part. Okay, here are the references we are using. Okay, thank you.
Okay, thanks, Mandeep. So we have some time to take up some questions, but before somebody else asks a question, I think Akash has had another question, but I didn't read it on time. So Mandeep, when Akash asked that are you using perturbation theory, you said yes. He is asking further, if yes, then how are you sure whether there are no more NLO which can suppress this term? Basically, it's asking if there can be higher order terms which are larger than the term that you are computing. Is that correct, Akash? You can unmute yourself and ask the question directly. Akash, can you please unmute and ask the question directly? So Mandeep, yeah, can you explain that? Do you think in your perturbation series there can be basically some higher order terms which dominate the term that you are computing?
Like we are calculating the amplitude up to the two loop level. So total amplitude is the sum of these three terms, right? M0, M1 and M2. In this tree level amplitude, this is only of the order of, I have already explained it, like E cube. This is E5 and this is E5 GS square, if I am correct. So when we take the square of this amplitude, this term will give us like E6 mod M0 square. This will give E10 mod M1 square plus E10 GS4 mod M2 square. Then 2 times real correction of the interference of M0 with M1, that is of the order of E8 plus 2 times real correction and the interference term of these two terms M1 with M2.
No, Mandeep, I think, I mean, the way he's asking question and the way you are trying to address, I think he needs to discuss with you. So he says that he would like to discuss with you, okay?
Oh, okay,
Yeah.
that is okay. You can come,
We
Akash,
are
anytime.
trying to answer from the power counting point of view of in
Yes.
the coupling.
Couplings, yes.
But yeah, that's your answer. I mean, I think he understands that, but he wants to discuss with you something more. He's worried
Okay.
about the terms that you contribute, that if you compute higher order terms,
Okay,
how do you
and
know that
next,
the calculation
and
itself will not be so large that it dominates the effect of the coupling itself?
okay,
Okay.
I
Yeah.
will discuss.
More questions to Mandeep? Okay, maybe I can ask once more. If you have any question, you can directly, you can unmute yourself and ask Mandeep. Okay, I believe there are no more questions. So, Arpit?
Yes, sir.
Yeah.
So thank you, Mandeep, for such a wonderful seminar. And
Thanks.
so we have an announcement. Yes. So in case you are interested in giving a talk in THEP Journal Club, please write to us, and we'll update you regarding the next week's meeting. And okay, see you all next week. Thank you.
Okay, thank you.
Thank you, Mandeep.